Hey everybody, getting into angular momentum and its conservation. So let's just recall a little bit about momentum. That was that lovely letter P. I think there might be one more item here that we should write out. But ultimately, right, we are going to have a rotational equivalent. Okay, we'll have a rotational equivalent to momentum. Okay, the angular equivalent for momentum, if translational or linear motion had P equals mv, we have capital L. Okay, this is for angular momentum. Okay. What's the equivalent of mass? That's I. The equivalent of velocity, omega. So if we're dealing with angular momentum, something rotating, and that has momentum, so you start something spinning, it wants to keep on spinning, right? And that's going to be based on its rotational inertia and its angular velocity. Well, Newton's second law could be written like this. Change in linear momentum, right? Or translational momentum over time, the rate at which the momentum changes. Now, the net torque, right, its angular equivalent, is going to be equal to the change in angular momentum over time, okay? And if you remember one more thing, okay, and that was impulse. How did we get impulse? That was net force times delta t, so net torque, right, times delta t is going to relate to this, and this would be an angular, right, impulse here. Okay, this is a very direct instruction. But if I apply a torque, right, for a certain amount of time, okay, I wish I had my tire, right? If I apply a torque for a certain amount of time, I'm going to get a change in momentum. Just like if we applied torque, a net torque over a distance, right? Over an angular distance at theta, and that would give us our work, right? Force times distance equals work. So there's a direct translation, okay, from all our linear work. Again, I talked about this in the last example, although you're not going to have that connection. Every one of our units, except for 8.1 and 8.2, right, talked about a previous chapter. Chapter 3 was constant acceleration. Well, we looked at constant acceleration equations, but rotationally. Okay. Chapter 4 was Newton's laws. It wasn't written like this, but force equals net force equals mass times acceleration. We had a net torque equals inertia, rotational inertia times angular acceleration. Chapter 5 is circular motion, so we've had a conversion to angular, like it was just a conversion from centripetal acceleration to rotational, right, in terms of rotational. Chapter 6 was energy, and we've been dealing with kinetic energy in 8.7, and now we're in momentum, 8.8, which refers back to chapter 7. Where we looked at Newton's second law in a different way, change momentum. Momentum, mass times velocity. And then we could get into an angular impulse, something that gets something spinning, okay? So what I wanted to show, I guess ultimately, as far as these direct equations, one equation, two equations, three equations, direct translations, okay? What we really got into in the momentum section was conservation of momentum. Okay, now we're not going to go as deep, okay, as that chapter. We talked about elastic collisions, inelastic collisions, conservation of kinetic energy, right? Made it an elastic collision, and when kinetic energy wasn't conserved, it was an inelastic collision. Ultimately, we're just going to go into conservational momentum, meaning the momentum in state 1 is going to equal the momentum in state 2. So the I omega 1 equals the I omega 2. Now, could this change this rotational inertia? Yeah, absolutely. This is the ice skater principle. I don't know if you remember them. So it's the spins that are phenomenal, right? They start their spins with their arms, legs out on one leg, and they're spinning, and then they bring it tight. Has the rotational inertia of the ice skater changed? Absolutely, it's decreased. So at first, large rotational inertia, or that inertia, with a slow angular speed, and then they reduce that angular rotation or that angular inertia, rotational inertia, and what happens to that speed? It just skyrockets. I'm going to see if I don't crash the system, and by taking a video of videos. Okay, if I crash it, sorry. Hopefully this recorded well enough. I will just link those videos in the 8.8 section. Okay, here we go. Let's see what we can do. I think this one's cool. Not much sound going with it. Lady spinning in space. There is no friction, right? Her rotational inertia is tight. Guess what she's going to do? Expand. And you'd think that would stop her, but there are no losses, and she tightens back up and she speeds up. Pretty cool. Okay, so I'll stop that one. We got University of Ohio. Oh, Ohio State University, sorry. I think I might give an extra credit for anyone who links me to a video of them demonstrating conservation of angular momentum. These are cool, and this is our last one. Hi, puppy. Sorry, my pup's kind of getting antsy. So cool. Look at that. So cool. Do it again. Do it again. Oh, he's not going to do it. Do it again. Oh, come on. So cool. Okay, just geeked out. I'm stopping there. So again, while we've got a lot of equations from former chapters, that translational momentum, there's a direct linear connection, L for angular momentum, and M is replaced with I, so that depends upon the shape. V replaced with omega, right? So this is your angular momentum equation. And then we've got other equations that follow in suit, okay? As far as net torque, change in angular momentum over change in time. You can get angular impulse against a torque that is causing a change in momentum, okay? But ultimately, I think our questions relate to conservation of momentum. The angular momentum before is equal to the angular momentum afterwards. And honestly, these I1, I2, it's only one shape, okay? In the past, we've had two elements colliding, and in this situation, it's one shape that can change their rotational inertia. So you've got an I1 and an I2, and those angular speeds, like, go back and forth, right? If I increase the I1, and I've got a small omega, if I decrease I2, the omega 2 has to shoot up, okay? I hope this is enough. I hope those demos were good, video in a video. And we'll see if we've got questions. Bye, guys.